One of the last lectures, we talked about the rocket equation and how the rocket equation can help us figure out how much delta V a rocket can produce, or how much mass, how much fuel mass you need to produce some sort of a delta V. But what we neglected to talk about is the fact that rockets have stages. Last time we used the V2 rocket, which has no stages, but this time we're going to talk about rockets that actually have stages. There are two reasons for rockets having stages. Reason number one is that you can drop mass on the way up. So basically you go up a little ways, then you drop a bunch of mass, and then you go up faster. That's because of force equals mass times acceleration. If we drop a bunch of mass and we apply the same force, our acceleration goes up. Reason number two is the physics of nozzles. The nozzles actually help us work differently in an atmosphere versus in space. Now, if you look at a rocket when it's working in an atmosphere, the plume of the rocket exhaust, the stuff coming out of the nozzle, when it's in the atmosphere, when it goes off of the launch pad, it's pretty confined. And that's because in the atmosphere, there's atmospheric pressure that's pushing on that exhaust, and it doesn't let it escape as much. And so the efficiency of the rocket plume is not as good in the atmosphere as when it gets into space. And if you see a picture of a rocket operating in space, the plume is very big and puffed out. And that's because it's designed to work really well in space. And so you maximize the exhaust velocity. So if we look at a Falcon 9 and we look at what the exhaust velocity is on a Falcon 9, for the first stage, it uses an atmospheric version of the Merlin engine, and its exhaust velocity is around 2,800 meters per second, pretty close to 3,000. The second stage uses a vacuum version of the Merlin engine, and that is about 3,400 meters per second. And so you get about a 20% increase in efficiency just by using different engines on the ground versus in space. So that's one of the reasons why you do two stages. The first stage has atmospheric versions of the engines. Then you get rid of that after you launch. And then when you're in space, you use the vacuum version, which gives you a higher velocity, exhaust velocity. And so you can get a better thrust from that. Now, dropping mass, basically, when you're going up, you start off with a very, very heavy rocket, and then you go up for a little ways, and then eventually you've used a lot of fuel, and so the fuel tanks in that first stage are empty. There's no reason to carry all of those empty fuel tanks and those engines anymore, so you just drop them. And then your mass is significantly less, and then you can fire off, and you can increase your acceleration significantly. So what we're going to do is we're going to go through some math of a two-stage rocket. We're going to call it the Peregrine 8 rocket because we're going to use sort of like Falcon 9-ish numbers, but we're going to sort of make up some stuff a little bit. All right, so the Peregrine 8 has two stages, and we need the dry mass and the wet mass of each stage because each stage has a bunch of fuel in it. Each stage has some engines, and so it has some mass, and it has a different exhaust velocity. So in stage 1, we have a dry mass of 25,000 kilograms, a wet mass of 400,000 kilograms, so it carries a lot of fuel, and an exhaust velocity of 2,800 meters per second. In stage 2, the dry mass is significantly smaller. Stage 2 is much smaller than stage 1. Its dry mass is about 4,000 kilograms, and its wet mass is 100,000 kilograms, and its exhaust velocity is about 3,200 meters per second. The payload that we're going to try to take to orbit, or we're going to shoot off the ground, is about 2,000 kilograms. That's pretty low for what the Peregrine 8 can carry to orbit, but we're just going to use that for simplicity. So now we have to go through a bunch of math using the rocket equation. And so we're going to sort of zip through this math a little bit. No one's expecting you to know how to do this math, but we're just going to go through it just so we understand what's going on. So when the rocket is sitting on the launch pad, its total mass is the wet mass of the first stage plus the wet mass of the second stage plus the mass of the payload. And that total mass is 502,000 kilograms. After it burns, it uses the fuel in the first stage. So that's going to be the dry mass of the first stage. But it's still carrying the wet mass of the second stage, and it's carrying the mass of the payload. So all we're doing is taking the wet mass of the first stage and turning it to the dry mass of the first stage. And then we come up with a total mass of 127,000 kilograms. So now we have that stuff when we can actually do the rocket equation. And we have to remember that the exhaust velocity for the first stage is 2,800 meters per second. So when we do that math, we have delta V is equal to the exhaust velocity times the natural log of the wet mass divided by the dry mass. We put in all those numbers and we come up with 3,836 meters per second. If you just took the Peregrine 8 and you had the first stage and you wanted to launch the second stage and the payload into orbit, you couldn't get into orbit because the first stage only gives you 3,882 meters per second. You need that second stage to actually get to orbit. So now if we do stage 2 burn, we completely drop the stage 1 dry mass. We literally drop the stage 1 dry mass. Then we have the wet mass of stage 2 is equal to the wet mass of stage 2 plus the payload, so that total is 102,000 kilograms. After it burns, we take the wet mass of the second stage and we convert that to the dry mass of the second stage. And that is 6,000 kilograms. All right, 4,000 plus 2,000. The 2,000 is the payload. So now we remember that the exhaust velocity is 3,200 meters per second for the stage 2. And when we plug this into the rocket equation, we get that the delta V for the second stage is 9,000 meters per second. So the second stage is super, super, super efficient. So when we combine stage 1 and stage 2, we just add those delta V's together. Stage 1 fires, it gives you delta V1. Stage 2 fires, it gives you delta V2. When we add those together, we get a total of 12,948 meters per second. The Peregrine 8 can actually launch 2,000 kilograms on an escape trajectory. We could launch this to the moon or, escape Earth and have it go somewhere else. It can take 2,000 kilograms and it can get away from Earth very easily with a 2-stage Peregrine 8 rocket. Now let's say what happens if it only had one stage. Let's get rid of the dry mass of stage 2. Let's just say that we build a larger stage 1 and we add all of the fuel from stage 2 into stage 1, okay? And so what we're gonna do is we say that the wet mass of stage 1 is the wet mass of stage 1 plus the fuel of stage 2 plus the payload, which is 498,000 kilograms. Then the dry mass is just the 25,000 of stage 1 plus the 2,000 of the payload. And that is 27,000 kilograms. But we have to remember that the exhaust velocity for stage 1 is only 2,800 meters per second, okay? So then when we do our math, we have delta V is equal to the 2,800 times the natural log. And then that gives us 8,155 meters per second. So if we only have one stage, we put all of the fuel into stage 1 of the Peregrine 8, we could only get 8,395 meters per second. But if we did it in 2 stages where we drop off stage 1, once we've gotten up a little ways and we got rid of all of the fuel, we drop that dry mass, then we could get 12,976. This 12,976, you could escape Earth with that. With the 8,395, you could barely get to orbit with that. And so a 1-stage Peregrine 8 would barely get you to orbit. A 2-stage Peregrine 8 would get you to escape Earth, much more capable. Why wouldn't we just take this and make 3 stages or 4 stages or 100 stages? You shoot a little bit of mass, then you get rid of that stage. You shoot a little mass, you get rid of that stage. Why not just do that over and over and over again? Well, each stage actually has these engines in it, and so it adds a little bit of mass. You have some overhead because you have these engines. What happens with the Falcon 9 is that they've done things quite smartly. They use the same engines in the first stage as they use on the second stage. So they manufacture 10 engines for a Falcon 9. 9 of those engines are used on stage 1, and 1 engine is used for stage 2. If they took that same engine and they used it for like a 3rd stage, then you take that pretty heavy rocket engine and you would want to apply it to something that's pretty small. And that doesn't make a lot of sense. So you'd have to manufacture a much smaller engine for a 3rd stage. And they don't want to manufacture a 3rd engine. They want to, or a different type of engine. They want to use the same engines for all of their stages. And they're big. And so you use 9 for stage 1, 1 for stage 2, and you have no stage 3. All right? So they balance basically the efficiency of these things and the manufacturing of the rockets, and they don't put a 3rd stage on. They just have 2 stages. Some rockets have 3 stages, but not very many rockets have more than 3 stages, just because the efficiency goes down after you get about 3 stages. So, in summary, rockets have stages, and they do that so they can shed mass and they can accelerate at a higher rate. They also do that because the efficiency of the engine is dependent on the atmospheric pressure. So when you're low down, you use sort of an inefficient engine that's optimized for atmospheres, and then you go up, you get rid of that engine, and then you change your engine to be one that's optimized for vacuum. It's best to switch to a different engine when you get above the atmosphere. So that first stage gets you above the atmosphere, and then you switch to the other engine. Most rockets use 2 stages for efficiency. Some use 3, and not many use more than that. Thank you very much.